through our last talk, 5 sessions and 23 talks. And I have to applaud our students and researchers for doing a great job of staying on time. As I said in a previous session, you know, faculty would never be able to do this, but our students and researchers can. So faculty just can't talk for 25 minutes. They need 50 or longer. So, so our last one is from IIT Kanpur is Shaman. Shaman?
Yes, ma'am. I am present, ma'am. Yes.
Okay. Great. So I'm going to stop sharing and you can share.
Yes, ma'am. Ma'am, my slide is visible?
Not yet.
Oh.
Doesn't seem to have started to share yet.
Okay, ma'am.
Here we go.
Yes, ma'am. Ma'am, my slide is visible?
No, right now we see your directory of files. You can double click on that PDF and then it should be ready to go.
No, it is visible, ma'am. No.
Nope, we're still seeing the directory.
Oh, now it is visible, ma'am.
Now it is visible. There you go.
Yes.
If you want to
yes.
make it, if you want to make it 100, yes,
yes,
it's visible. Perfect. All right.
Yes, ma'am.
There you go.
Hi, everyone. I am Chaman Lal. I am a PhD student at IIT Kanpur, and today I am going to present. My topic of presentation is a fair incentive scheme for smart inverters participation in voltage control. And my theme of research is grid connected solar PV. And here I am taking problem is voltage control in low voltage distribution systems with solar PV. This diagram shows that this is a distribution transformer and this is overhead line. During normal, when power flow from source to load, there is a voltage drop in the line, and generally we observe low voltage at the extreme end of the line. And when the solar power generation is high, there is a reverse power flow from load side to source side. It causes high voltage rise problem at the extreme end of the overhead line. So I am considering this problem voltage control in the low voltage distribution system, and I have considered only solar inverter to control the voltage. And this diagram shows the PQ capability of a solar inverter. So this side, positive side, shows that when there is a low voltage scenario, inverter can supply reactive power and can avoid the low voltage scenario. Similarly, this is negative side. When there is a high voltage rise scenario, inverter can absorb reactive power and can maintain the voltage. But during high generation of solar power, reactive power capability is low. For such type of scenario, we need overrated inverters to control the voltage so that we can absorb some reactive power. Or other option is we have to curtail some active power generation. So it is a simple test system for the analysis. Suppose number one is a distribution transformer, and these are the nodes where load demand and solar inverters are connected. Suppose the solar generation is high and there is a reverse power flow from the 27 to toward 27 to from 27 to 1 or 14 to 1. So there is a reverse power flow, or during such type of reverse power flow there may be a high voltage rise scenario. Suppose there is a high voltage rise scenario, and these two nodes, suppose number 4 and number 26, they are injecting equal active power injection. Suppose that is 6 kilowatt, they are injecting equally 6 kilowatt. So this is a question that this inverter, one option to control the voltage is they should absorb reactive power equally or unequally. Or second question is here that they should curtail active power equally or unequally. So from this analysis we will find out the answer. So to do the analysis, I have modeled is a three-phase optimal power flow in rectangular coordinates, and it is solved as a interior point, is solved by interior point, and these are constants. This is injection, P injection, Q injection at the nodes, and this is power flow limit, voltage constants, active power curtailment limit, proportional active power curtailment limit, and this is the reactive power capability limit of inverter. So first I start my analysis with the reactive power analysis. So for this case, the rated active power output of inverter is taken 7.5 kilowatt, and overrated inverter, 10% overrated inverter is considered, so that it can absorb reactive power during high generation of solar power. So these are simulation results, and this shows that this is a high voltage rise scenario, and where solar power generation is higher than the load demand, and there is a reverse power flow. This negative shows that power is flowing from load to source, and reactive power is negative. It means reactive powers are absorbed by inverter, and we can observe that when inverters are absorbing equal reactive power and unequal reactive power, we can find that when there is a unequal sharing, it requires less reactive power absorption. So it shows that this unequal sharing is optimal. So this figure shows the how the nodes are observing reactive power. So when there is unequal sharing, only some inverters are observing reactive power. Why? Because at this extreme nodes are more sensitivity. When we give same amount of reactive power, same amount of when they observe same amount of reactive power by at the extreme nodes or these nodes, here sensitivity is high. So this is optimal. So these nodes are injecting more reactive power. So what happened when some inverter gives reactive power? So it causes power loss in the inverter, it causes life reduction in the inverter, and that customer has to purchase overrated inverter. So that customer should get incentive. If that customer is supplying reactive power to maintain the voltage of the grid, that customer should get incentive. So the reactive power incentive scheme should consider all the components: power loss components, life reduction components, and this is a overrated inverter. Suppose there is one inverter of rating 7.5 kVA of cost 77,875, but if you purchase 10% overrated inverter, it is 8.25 kVA of cost 81,812. So this shows that it needs 4,000 more rupees. So it should be compensated. And this table shows the simulation results for some scenario where inverters absorb some reactive power, and uh, corresponding cost of power loss and cost of life reduction is given. So this was the analysis for reactive power analysis. But I said that suppose some inverters are not overrated, or maybe there is a energy storage is not present, or this high voltage die scenario is occur only for some days of the year. So it may be a good option to curtail some amount of active power, and we can maintain the voltage of the system. So active power curtailment analysis also important. And same question, equally and unequally active power curtailment, what is optimal? And for this analysis, I have assumed the reactive power output of solar is 8.5 kilowatt. So these are simulation results. So these are the voltage at the distribution transformer, solar generation and load demand, and this is the high voltage rise scenario where the solar generation is greater than the load demand, and there is a reverse power flow. This negative value shows the reverse power flow, and it shows that that when we do unequal curtailment by inverters, it is optimal. It is 39.99, 57.46. And this is a pictorial representation. What is the active power curtailment by inverters? So same reason, sensitivity of the extreme nodes are higher. So they are only curtailing, and their cumulative active power curtailment is less. So it is optimal. So, but if someone curtail active power, it is a loss of economy. So it should be incentivized. But active power curtailment should be fair for renewable power producer and utility, renewable power injection and renewable power curtail. So these things should be considered while formulating incentive scheme for active power curtailment. So one formula is proposed that one formula is proposed to calculate the price of the renewable energy. So this formula says that it reduce the actual cost of renewable energy so that it can give to the participant who is curtailing active power. For example, suppose it is a scenario. Suppose total solar power generation is 195 kilowatt, and total solar power actual, but it is injection is 186 and 8.1 kilowatt are curtailed. Actual cost of solar energy is 6, and by using that formula I reduce to 5.75 so that I can pay the participants who are curtailing active power. Its cost is 47, and it is 1075. So total cost is 1121, and it is same previously without a scheme and with a scheme. It shows that it does not increase the burden on the utility. So conclusion of the analysis, that unequal active power curtailment and unequal reactive power injection are found optimal. And this analysis shows that only some inverters with active power curtailment control or reactive power injection control at the extreme nodes are sufficient to control the voltage of the system. And I propose the APC incentive scheme, which is fair for distribution utility, renewable energy producer, and participants of active power injection and active power curtailment. And when we have less number of overrated inverters, it also reduces the investment required for overrated inverters. So these are benefits. Thank you.
All right, thank you very much for your presentation. So we'll open it up to questions.
Hello, can you hear me?
Yes, we can.
Yes, sir.
Yeah. So one quick question here is, how do you differentiate the active power curtailment when there is overproduction in comparison to the case where you are saying that, okay, active power curtailment is actually done for the I can say voltage support. So how do you differentiate that?
Yes, over generation and sir, active power curtailment for voltage control.
Yeah, because sometimes the utility says, okay, you should not feed more than 10 kilowatt hour. Okay, then they have
Yes,
to
sir.
curtail their production. If solar is generating too much of power beyond 10 kilowatt hour, then they just curtail it. But when there is like you mentioned, when there is a need to restore the voltage within the normal range, then they have to curtail the active power so that they inject the reactive power in order to do that. So how does the algorithm will differentiate both the scenarios?
Yes, sir. Sir, I have only considered the scenario of voltage control, but if participant is curtailing active power, he should get some incentivized, and so I am differentiating that if I want to control the voltage, how it should be optimally curtailed. So I have not considered the over generation point of view. Yes, sir.
Yeah, correct. But whatever the cost function you proposed it, but it only takes care of the active power, but that does not know whether the active power curtailment is from the overproduction or from the reactive power support.
Yes, sir. Sir, but if utility is asking to curtail active power to the participant, and so there should be some reason why he is requesting. Yes, sir. So
Yeah, got
So
it.
what I feel, Sanjeev, one is the load management problem, like which is happening all the time. Depending on the loading value, the generation is being balanced. Second is when you are doing the volt war control, and there is a need to, you don't have any other source to control the voltage, and you are now banking on the inverters or solar fed inverter to curtail certain real power. So that is coming as an additional command to control the voltage. Am I right, Chamanlal? Or
yes, yes, sir.
yeah. So that is my feeling actually. So the two are different. One is the continuous load management. Second is when you are solving the volt war control. But how? I mean, another. Arya, do you have any other question?
No, I think I'm good. Thank you, Professor.
Okay. Then I have one question. You said that unequal curtailment is the most optimal.
Yes.
That's fine. I think it all depends on the sensitivity of the real power output of sensitivity of voltage which you are controlling with respect to real power injection from the sources. So maybe some sensitivity information also you can utilize. Which one will be more effective in controlling the voltage? So
Yes,
unequal becomes important when the sensitivity are different, is it not? Otherwise,
yes, sir.
suppose
Yes.
the two sources are equally at distance from the point where you want to control the voltage, and
Yes.
sensitivity is same, you may go for equal curtailment.
Yes.
So it all depends on the sensitivity.
Sensitivity.
Yeah. No, you can say no also. Okay.
Yes, I will check it.
Good.
Okay, do we have any other questions?
I have a question.
Yeah, go ahead.
I want to know if the inverters have communication each other, or how do they share the load, or how do you manage that? So I saw that you are controlling the voltage, right? But
Yes, yes, I am controlling voltage, and here I am using optimization, so I know the information of all the nodes.
so based on optimization, you define which inverter will control the voltage, or are you communicating with some link between them to see, like for instance, the third inverter is as actually restoring the voltage compared to the first one, so they don't interact each other. Is that correct?
Yes, sir. First, I am taking the measurement, then optimization solved such that which inverter should curtail or which inverter should absorb the reactive power to maintain the voltage, and so that this optimal decision can be taken. Yes.
Thank you.
Yes.
for questions? All right. Well, thanks again to everybody to our 23 speakers over the last 5 sessions. We really appreciate all the input, all the presentations, and particularly the Q&A. The folks that have asked different questions. We will be, as I mentioned, we will be posting, oops. Oh, okay, thanks. So we will be posting the information from all the speakers, or excuse me, we'll be posting the presentations. And our plan is right now to try to post them by presentation. So to give people a chance to look at particular ones. And if you have any questions for the speakers, please get back to them. But again, we really appreciate all the presentations and all the participation over the last 5 sessions. So for our US colleagues, we say good evening. And for our Indian colleagues, we hope you have a great Thursday. So thank you everybody for participating.
Well, thanks, Noel. Great job done. Yeah. Thank you.